Unit vector. Welcome, everyone. Today, we are going to begin a new topic in vector algebra, the unit vector. Now, as you know from our previous lessons, a vector is defined by both its magnitude, which is its size or length, and its direction. However, in many advanced mathematical and physical problems, we often encounter situations where the actual size of the vector isn't the most important part. Instead, what really matters is the specific direction in which the vector is pointing. To handle these specific cases, we use a very special type of vector called a unit vector. So, what exactly makes it special? By definition, a unit vector is a vector that has a magnitude of exactly 1 unit, or what we sometimes call unity. Think of it this way: its primary purpose is to act as a pure indicator of direction in space. Because its length is always exactly 1, it allows us to specify a direction without adding any extra weight or additional length to our calculations. This keeps our math clean and focused solely on the orientation. In the next slide, we will look at the specific notation we use to distinguish these from regular vectors. Notation and symbolism. When we are talking about a general vector, we use the standard notation, which is the letter A with an arrow on top, written as a vector. This represents a vector that can have any magnitude or length. However, when we want to talk specifically about the unit vector that points in that same direction, we change the notation slightly. Instead of that arrow, we place a small hat symbol on top. We write this as a cap. So, to summarize the difference, we have a vector for the general case and a cap for the unit vector. It is crucial to understand the relationship between these two. Even though they look different, a cap points in the exact same direction as a vector. The only difference is the scale. We have essentially taken the original vector and scaled its length, either shrinking it down or stretching it so that its magnitude is exactly 1. Now that we understand the basic concept of what a unit vector is, let's look at how we actually write them down on paper. This is very important for your exams, as notation is key in vector algebra. In the next slide, I will show you the mathematical formula we use to perform this scaling process. How to find a unit vector. So, how do we actually transform a standard vector into a unit vector? To obtain a unit vector from any non-zero vector, arrow, we simply divide the vector by its own magnitude. You might hear this process referred to by a more technical term. It is known as normalization. Essentially, we are normalizing the length to exactly 1 while keeping the direction unchanged. Let's look at the mathematical formula that represents this. The formula is expressed as a cap equals the vector arrow, all divided by the magnitude of arrow. To be very clear about the components here, a cap represents our resulting unit vector. Arrow is our original starting vector, and the vertical bars surrounding arrow represent the magnitude or the length of that original vector. Now that we understand what a unit vector is and how we denote it with that cap symbol we saw on the previous slide, let's look at the actual procedure for finding one. In the next slide, I'll give you a real-world analogy to help you visualize why this division is so important, and then we will walk through a concrete numerical example to see this formula in action. Real-world analogy. Now, I know the mathematical notation and the formula for normalization might seem a bit abstract, so let's step away from the symbols for a moment and look at a real-world analogy to help this concept click. Imagine you are giving someone directions to a hidden treasure. If you were to tell them, walk 10 kilometers north, you are providing what we call a full vector. In this case, you've given them both a magnitude, which is the 10 kilometers, and a specific direction, which is north. However, imagine you don't want to tell them how far to go, but you simply want to point your finger in the direction where the treasure is buried. In this scenario, your pointing finger acts exactly like a unit vector. Notice that your finger doesn't tell the person how much distance to travel. Its only job is to specify the direction they must move in. This perfectly mirrors what we discussed in the previous slides. The magnitude is essentially stripped away, leaving us with just the direction. This principle is used extensively in physics. For instance, when we define the axes of a coordinate system, we use unit vectors like I hat, j hat, and k hat. Just like our pointing finger, these vectors serve as the fundamental building blocks to indicate direction along the x, y, and z axes without adding any extra length. Now that we have a conceptual grasp of what a unit vector represents, let's move on to the next slide, where we will work through a concrete mathematical example to see how to actually calculate one. Step-by-step mathematical example. Let's find the unit vector, which we call a cap, for the given vector which is 3i hat plus 4j hat. To do this, we will follow a clear three-step process. Step 1, we need to calculate the magnitude of our original vector, a. As we discussed in the previous slides, the magnitude represents the length of the vector. To find this, we use the magnitude formula, which is the square root of x squared plus y squared. Plugging in our specific values, we get the square root of 3 squared plus 4 squared. When we square those numbers, we get the square root of 9 plus 16. Adding those together gives us the square root of 25. And as we know, the square root of 25 is exactly 5, so the magnitude of our vector is 5. Step 2, now we apply the unit vector formula that we saw earlier. This is the process of normalization I mentioned. We take our original vector, and divide it by its magnitude, which we just calculated to be 5. This looks like a cap equals the vector, divided by the magnitude of which is the same as writing 3i hat plus 4j hat, all over 5. Step 3, finally, we simplify the expression. To do this, we simply distribute that division across both components of the vector. This gives us 3/5 I hat plus 4/5 j hat. If you prefer working with decimals, you can write this as 0.6 I hat plus 0.8 j hat. Notice that this new vector, a cap, still points in the exact same direction as our original vector, but its length is now exactly 1. Now that we have understood the theory and the concept of normalization, let's put everything we've learned into practice with a concrete mathematical example. As we move to the next slide, I want you to pay close attention to the common pitfalls to ensure you don't make these same errors when working on your own. Common mistakes to avoid. First, be very careful not to confuse the notation for a with an arrow over it and a with a hat over it. It is a very common mistake to use these symbols interchangeably. Always remember the distinction we discussed earlier. A with the arrow represents the full vector, which carries both magnitude and direction, whereas a cap, that's the one with the hat, represents only the direction, with a fixed magnitude of exactly 1. Second, watch out for the mistake of forgetting the magnitude. A frequent error is simply writing down the direction components without actually dividing by the magnitude. I must emphasize this. A vector is not a unit vector unless its magnitude is exactly 1. If you skip the division step, you haven't completed the normalization process. Finally, a technical but crucial point. When you are performing the calculation, ensure you are dividing the vector by its scalar magnitude, which we write as the magnitude of a, the vector, inside 2 vertical bars. Do not attempt to divide the vector by another vector. You are scaling the vector down by a single number, not by another directional component. Now, before we wrap up our lesson with the final summary, I want to pause and highlight some common pitfalls. I've seen many students stumble on these specific points during exams, so please pay close attention. Keep these errors in mind, and you'll be well on your way to mastering unit vectors. Now, let's look at our final key takeaways to solidify everything we've learned today. Key takeaways. First and foremost, remember that a unit vector is a very specific type of vector. It is defined by having a magnitude of exactly 1. Second, pay close attention to your notation. To distinguish it from a standard vector, we use what we call a cap symbol. So, instead of writing a with an arrow on top, we write a cap. This small change in symbol tells anyone looking at your work that the magnitude is 1. Third, keep this fundamental formula at the front of your mind. To find that unit vector, you take the original vector, and divide it by its own magnitude, which we write as the magnitude of in vertical bars. This process of normalization is what scales the vector down to a length of 1. Finally, never forget the why behind this concept. We use unit vectors primarily to specify a direction in space without any extra weight or length attached to it. They are our tools for pure direction. All right, we have reached the end of our lesson. Before you move on to your practice problems, let's quickly recap the key takeaways from today's session to ensure everything is clear. If you have mastered these points, you are well on your way to mastering vector algebra. Great job today.